Welcome to a series called What the Hell is Organic Chemistry? This is the series where I help people who are struggling with organic chemistry. My name is Zeanium, your host and guide. Today we're diving into what the hell are resonance. In this video you will learn all the tools you need to draw resonance structures. And no, this is not optional. Resonance is the topic. It shows up everywhere, every chapter, every reaction, and yes, even in your nightmares if you choose to ignore it. So you cannot get an A in this class without mastering resonance. This is not a suggestion, it's a warning. So what the hell is resonance? In our bond line drawing video, we learned that it's the best way to draw molecules. They're fast, they're clean, but plot twist, bond line structures are good, not perfect. In fact, no drawing method can fully describe a molecule using just one picture. And this is where the problem begins. Resonance is our solution to the problem. Instead of forcing one drawing to do all the work, we use multiple drawings to represent one single molecule. These drawings are called resonance structures. Then we take all those drawings and mentally mash them together into one real molecule. It's like the chemistry's version of combine all the clues and see the full picture. So to make this actually make sense, let's use an analogy. Imagine your friend asks you what a nectarine looks like. Problem, they never seen one and you're not an artist, so stick figures are your limit. So you say, picture a peach in your mind, now picture a plum. A nectarine is basically the best of both worlds. The inside tastes like a peach, but the outside is smooth like a plum. Now smash those two images together in your brain, that's a nectarine. Important clarification, a nectarine does not switch back and forth every second like, today I feel peachy, no wait, plum energy. A nectarine is a nectarine all the time. Picture of just a peach isn't enough, picture of just a plum isn't enough. But when you imagine both at the same time, you actually understand what a nectarine looks like. The problem with drawing molecules is basically the same problem as the nectarine. No single drawing can probably show how the electron density is spread out across the molecule. So we stop trying to force one picture to do everything. Instead, we draw multiple resonance structures and then mentally combine them into one real molecule, just like you did with the peach and plum. One molecule, multiple drawings. So an example could be this one. The compound has two resonance structures, so we separate them using a straight double-headed arrow and wrap them into brackets. So this is a double-headed arrow and this is a bracket. And that arrow and those brackets are chemistry's way of saying, relax, it's just one molecule. The molecule is not flipping back and forth between those structures like it's indecisive. Nothing is switching. Nothing is moving. These are just different drawings used to describe the same molecule. We're going to walk through plenty of examples and practices that show how to use resonance rules to spot regions of electron richness and electron poverty. So reactions stop feeling random and start making sense. Buckle up. So early in this course, you might see problems like, here's one drawing, now draw in the other resonance structures. Simple enough, feels manageable, you're calm, but later on, the training wheels comes off. At that point, it's just assumed that you can look at a structure and immediately draw all of its resonance structure. No hints, no mercy, and if you can't actually do that, yeah, future you is gonna have a bad time. So how do you actually draw all the resonance structures of a compound? Simple. You learn the tools to make it possible. Curved arrows. Now, here's where people get confused. So listen closely. These arrows do not represent an actual process. Electrons are not moving. Nothing is happening in real time. This matters because later in the course, you'll use curved arrows for reaction mechanisms. And those arrows do show electron flow. Every curved arrow has two parts. And yes, both of them matter a lot. Tail shows where the electrons are coming from. The head shows where the electrons are going. So next, we need some rules about where arrows are allowed and where they are absolutely not allowed. So the tail must start from a place that actually has electrons. As an example, consider the following resonance structure. So how do we get from the first structure to the second one? So this double bond right here, this double bond right here has been moved over here. And this is a classic example of electrons coming from a bond. So let's draw the arrow that shows the electrons leaving the bond and going off to form the other bond. So I drew it right here. Now let's see an example where electrons come from a lone pair. It will be like this. So the oxygen has a lone pair which just hops over to that bond, single bond, which creates a double bond. So never draw an arrow that comes from a positive charge. The tail of an arrow must come from a spot that has electrons. So the head of an arrow must point directly between two atoms if those electrons are going to form a bond. So basically just like this. Or it must point to an atom to form a lone pair, just like this. Now that we know what curved arrows are, but how do we know when to use curved arrows to push electrons and where to push them? First, we need to learn where we cannot push electrons. There are two important rules that you must never violate when pushing arrows. They are called two commandments of drawing resonance structure. Those shall not exceed an octet for second row elements. By definition, resonance structures must have all the same atoms connected in the same order. You cannot do this. And there's a simple way to ensure that you never violate this rule. Number 2, never exceed an octet for second row elements. Elements in the second row, carbon, nitrogen, oxygen, and fluorine, all have exactly 4 orbitals in their valence shell. That's it, 4 slots, no expansion pack, no DLCs, nothing of that. Each of those orbitals can do one job, form one bond or hold one lone pair. That means they can never have 5 or 6 bonds. 4 is the absolute maximum. The central atom physically cannot form another bond. It doesn't have the 5th orbital available. So the examples are pretty obvious when everything is drawn. But bond life drawings loves to hide things. Like I said in the previous video of bond life drawings, hydrogens aren't shown. And half of the time the lone pairs aren't either. So that's where people get tricked. You have to train yourself to see the hydrogen atoms and to recognize when you are exceeding an octet. This kind of looks right? Well, but once you count the hydrogens, the problem jumps out immediately, because that arrow will leave a carbon atom with 5 bonds, and that's illegal. Carbon absolutely does not have the budget of that. From now on, we'll call the second commandment the octet rule, but don't get too happy with it. There's an other important detail. For resonance structures, the octet rule is only violated if a second row element exceeds an octet, but having fewer than 8 electrons, that's basically allowed. So this carbon atom does not have an octet. This drawing is perfectly acceptable even though the central carbon atom has only 6 electrons around it. So let's get some practice. So we have this practice problem. For each of the problems below, determine which arrows violate either one of the 2 commandments and explain why. You can see that this curved arrow violates the octet rule. So because nitrogen cannot have 5 bonds, this curved arrow violates the octet rule. The second commandment, because nitrogen cannot have 4 bonds and 1 lone pair. This curved arrow violates the octet rule because carbon cannot have 5 bonds. So we have a lone pair that jumps to a bond. So this curved arrow violates the octet rule because carbon cannot have 5 bonds. A bond hops to the oxygen, which then informs a lone pair, which is a yes, because then it doesn't violate any of the 2 commandments. Now that we know how to identify good arrows and bad arrows, we need to get some practice drawing arrows. If you're given 2 resonance structures and asked to draw the arrow or arrows that connect them with them, don't panic, the move is pretty much simple. So compare the 2 structures and look at what appears and what disappears. A bond that shows up, a bond that vanishes, a lone pair that appears, a lone pair that disappears. So in this example, no lone pairs disappear, but a double bond does. That's your clue. The electrons are coming from that bond, so the tail of an arrow goes on the double bond. And in this example, a new lone pair shows up at the oxygen atom. That's your destination. The head of an arrow goes there. So a tail from what disappears, a head to what appears. So it's basically gonna look like this. So the arrow jumps, so the double bond jumps to the oxygen, which creates a lone pair and 2 formal charges. And the carbon that lost the bond gives a positive charge, so it's missing an electron. And the oxygen that gained the lone pair gets a negative charge. It gains extra electrons. Draw curved arrows that convert the first resonance structure below. So we can see that a lone pair disappears and gets to a double bond with the oxygen. This bond disappears and become a negative charge. So basically, easily, will be like this. Just gonna draw it all over again so you can kind of get double-headed arrow when talking about resonance structures. That's important. There we go. I think some lone pairs. So the arrow, we know that the oxygen is losing a lone pair, so the lone pair goes right here. Boom. And the double bond creates a negative charge on the carbon, which means it hops right here. Formal charges in resonance structures. So at this point we know how to draw good arrows, and more importantly how to avoid drawing bad arrows. But now it's gonna be difficult. Now we need to start drawing the resonance structures ourselves, even when they are not handed to us. So let's look at an example. One of the lone pairs on oxygen drops down to form a bond, while the CC double bond gets pushed up to become a lone pair on the carbon atom. So when we apply the rules for assigning formal charges, we see that oxygen ends up with a positive charge while the carbon gets a negative charge. In fact, if you forget to draw the formal charges, then you're missing the whole point of resonance. Notice the negative charge on the carbon atom. That single symbol tells us something huge. This carbon is a site of high electron density. It's electron rich. It's reactive. And here's the key point. You will never notice if you only looked at the original drawing of the molecule. So, without resonance and without formal charges, that information is completely hidden. This is exactly why we need resonance. So pay attention what the arrows are actually saying. Oxygen starts with a lone pair, 2 electrons that fully belong to oxygen. When that lone pair is used to form a bond, those 2 electrons are not shared. One counts for oxygen, one counts for carbon. Bottom line, oxygen just lost an electron. And when an atom loses an electron, it picks up a positive charge. That's why oxygen ends up positively charged in the resonance structure. A similar analysis for this carbon atom on the bottom right shows that it will get a negative charge. For each of the structures below, draw the resonance structures that you get when you push the arrows shown. Be sure to include formal charges. So we see here an arrow, a double bond goes to a positive charge carbon, which means it's gonna look like this. It goes there, and then the positive charge will remain up here. What about this one? We see that a lone pair goes to that bond, and then the other double bond jumps off, basically. So it's gonna look like this. It jumps up, so it's gonna have a negative and this up here like this. Yep. The nitrogen has a lone pair which hops to that single bond, and then the double bond in the ring jumps to this way to the right, and then it hops there. So it's basically gonna be like this. There we go. Okay, so we have a double bond that jumps to the nitrogen bond, and then we have a double bond goes to the oxygen, which gives another lone pair. So basically it's gonna look like this. 1, 2, 3, 4. Yeah, so it's missing one electron. Yep, that's right. At this point, we got all the tools. We know why resonance structures matter and what they actually represent. So let's go through these 3 steps one at a time. So starting with step 1, converting lone pairs into pi bonds. So let's see this example right here. So we draw an arrow that brings the lone pair down to form a pi bond, just like this. This does not violate either of the 2 commandments. We did not break any single bonds, and we did not violate the octet rule, so this is a valid structure. What about this? Notice that we cannot move the lone pair in another direction, because then we will be violating the octet rule. And let's try again with another example, like this one. So the arrow goes, the lone pair goes to the double bond, which already, like, what the hell? It violates the octet rule completely, and the carbon atom will end up with 5 bonds. So we cannot push the arrows that way. And there is no way to turn a lone pair into a pi bond in this example. Don't do that. Okay, so now let's move on to step 2. Converting pi bonds into lone pairs. So we try to move the double bond to form a lone pair, and we see that we can move the bond in either direction. So either in this or either in this. And neither of these structures violates the 2 commandments, so both structures above are valid resonance structures. However, the right structure, although valid, is not a significant resonance structure. For step 3, converting pi bonds into pi bonds. So let's consider the following examples. And if we try to push the pi bond to form another pi bond, we find the following, like, you can't do this. This one doesn't violate the octet rule, so we can do that. And the arrow on the bottom this one right here, will therefore provide a valid resonance structure. So it will be like this. The arrow jumps to the positive charge, which just creates a positive charge over there. Now that we have learned all 3 steps, we need to consider that these steps can be combined. Sometimes we cannot do a step without violating the octet rule, but by doing 2 steps at the same time, we can avoid violating the octet rule. For example, if we try to turn a lone pair into a bond in the following structure, we see that this will violate the octet rule. At the same time, we also do step 2, push a pi bond to become a lone pair, then it works. So if we add 2 arrows, it works. So we cannot move this double bond to become another bond unless we also move the CO bond to become a lone pair. And in this way, we're truly pushing the electrons around. Drawing resonance structures by recognizing patterns. There are 5 patterns that you should learn to recognize to become elite at drawing resonance structures. So, start with the first one. A lone pair next to a pi bond. So we have some examples here. Next to means that the lone pair is separated from the double bond by exactly 1 single bond, no more or no less. And you can see this in all of the examples below here. At each of these cases, you can bring down the lone pair to form a pi bond and kick up the pi bond to form a lone pair, just like this. And notice what happens with formal charges. When the atom with the lone pair has a negative charge, then it transfers its negative charge to the atom that will get a lone pair in the end. So it will be like this. The lone pair hops on to the single bond, and the double bond, pi bond, will jump off to the carbon. When the atom with the lone pair does not have a negative charge to begin with, then it will end up with a positive charge in the end, while the negative charge will go on the atom getting the lone pair in the end. So remember the conservation of charge. So let's do a little practice. Draw the resonance structure of the compound below. So we notice that this is a lone pair next to a pi bond. Therefore, we draw 2 curved arrows, one from the lone pair to form a pi bond and one from the pi bond to form a lone pair. So it's gonna be like this. It's pretty simple. So that means it gets a double bond. That's a very shaky double bond. And yeah, so look carefully at the formal charges. The negative charge used to be on oxygen, but now it's moved to carbon. So yeah, that's basically the exercise. Number 2, a lone pair next to a positive charge carbon atom. So we have some examples right here, and both examples exhibit a lone pair next to a positive charge carbon. And in each case, we can bring down the lone pair to form a pi bond. And notice what happens with the formal charges. When the atom with the lone pair has a negative charge, then the charges end up canceling each other. And when the atom with the lone pair does not have a negative charge to begin with, then it will end up with a positive charge in the end. So we have an arrow, we have a positive charge carbon atom. That means it goes over here. And then it gets a plus charge right here. Okay, so it has a negative charge, that means it has 2 lone pairs. And then one of the lone pairs just jumps on here, jumps right here. And this gets... Okay, number 3, a pi bond next to a positive charge carbon. And these cases are very easy to see, like the example right here. We only need 1 arrow, so going from the pi bond to form a new pi bond. And notice what happens to the formal charge in the process. It gets moved to the other end, so just like this. And it is possible to have many double bonds in a conjugation. This means that we have many double bonds that are each separated by only 1 single bond next to a positive charge. So basically like this. And when that happens, we push each of the double bonds over one at a time, just like this one right here. And it is not necessary to waste time recalculating formal charges for each resonance structure because the arrows indicate what is happening. So think of a positive charge as a hole, a place that is missing an electron. When we push the electrons to plug up the hole, a new hole is created nearby. In this way, the hole is simply moved from one location to another. Notice that the tails of the curved arrows are placed on the pi bonds, not on the positive charge. Number 4, a pi bond between 2 atoms where one of those atoms is electronegative. So nitrogen, oxygen, etc. So let's see an example. We have an example right here. And in cases like this, we move the pi bonds up onto the electronegative atom to become a lone pair. So like this, we saw many times. The pi bond goes up to the oxygen, which creates a lone pair. Notice what happens with the formal charges. The double bond is being separated into positive and negative charge, and this is the opposite of what we saw in the second pattern we looked at, where the charges came together to form a double bond. So yeah, that can happen too. So let's practice a bit. We are gonna draw the lone pairs on the nitrogen, and we see that this can hop here, then it gets a negative charge with negative charge and a positive charge here. Let's draw the lone pairs again. A pi bond can jump to the electron negative atom, which is oxygen, and yes. Number 5, the final one. Pi bonds going all the way around the ring. So whenever we have alternating double bonds or single bonds, we refer to the alternating bond system as conjugated. So a conjugated double bond. When we have a conjugated system that wraps around in a circle, then we can always move the electrons around the circle. And it doesn't matter whether we push our arrows clockwise or counterclockwise. Either way, it gives us the same result. Each of the following structures, draw the additional resonance structures. Let's start with this one. So this structure has a CN bond, we can see. So we can draw a curved arrow that pushes the pi electrons up onto the nitrogen atom. So generating a positive charge on the carbon atom and a negative charge on the nitrogen atom. So let me draw all the lone pairs first. Let me draw arrow goes up to nitrogen, which just turns. And now what we can do is to fill that hole. You can see that positive charge, we can fill that up. So we can just move this here. Draw it all again. That is our first resonance structure. Let's do this one. So the structure shown has a pi bond next to a positive charge. So we can draw one curved arrow that pushes the pi bond over. The new positive charge is once again next to a pi bond, so we can draw the third resonance structure. So it's basically just fill the hole. So we're gonna move this up here, which creates this right here. And then there's a hole right here, which this can attack. And this goes up there, so we get, and then the positive charge is over there, chilling. Now we have the third one. This structure has a positive charge next to 2 different atoms that each has a lone pair. And we can start by pushing a lone pair either from oxygen or from nitrogen. Either way, we can still generate 2 additional resonance structures. So we're gonna fill the hole up here. This gets a positive charge. Lone pair can go up here. And this double bond can fill the hole again. There we go. This is the resonance structure. This one, the structure shown here has an alternating single bond and double bonds in the ring. So we can push all the pi bonds to generate a new resonance structure. And this structure has a pi bond next to a positive charge. So we can draw one curved arrow that pushes the pi bond over. And then the new positive charge is once again next to a pi bond, and then we can draw the other resonance structure. And then, yeah, let me show you. It will be like this. Still positive charged. This is here. This is here. And this is here. And then the positive charge up here. And then it has there. Then we can move this to fill the hole up here. This go up here. The positive charge go down here. But there's also this one, which we can fill up the hole. And there we go. There we go. Yeah, that's the resonance structure. Let me draw the lone pairs. There we go. This lone pair just goes to this one to fill up the hole. And yeah, so it's gonna be a double bond. And this has a positive charge. Yep, that's that resonance structure. I'm gonna draw all the lone pairs. So pi bond could go up here and a negative charge, and a positive charge right here. This goes up here, form this compound. Negative charge here. There we go. And that's that resonance structure for that molecule. Drawing all the lone pairs. So this goes up here. So it's gonna be like this. Positive charge. Lone pairs party up there. To fill the hole, we use this double bond here, over here, there, and then positive charge atom, and the lone pair party up here. There we go. that's the resonance structure for that molecule. We're gonna do the same principle as we always do. Draw the lone pair first. This lone pair can hop over here to fill the hole. And that means it's gonna be like, oh, I have the hiccups now. It's gonna be like this. Double bond here, boom, and positive charge. Yep, that's it. Okay, so we have this molecule. We have a lone pair, so that lone pair goes up here. So this double bond goes up there. It will look like this. It goes there. That means it has a negative charge. It has a bond here, and then we can do this hops here, and this hops there. So it's gonna look like this. Okay, so this goes there, and this becomes this. Yeah, that's it. Repeat the boss. Again, remember to draw out the lone pairs. So it has here, we need to fill a hole. Since it's a positive charge carbon atom, we just do this, and then it's gonna turn us into this. There we go. And then we get a positive charge. And that's basically the molecule. Oh, sorry, the resonance structure for the molecule. The finale. It's gonna be like this. We draw all the lone pairs, and the lone pair of a halide is a lot. There's 3 of those. So we can move one up here. There we go. And then it will turn out into this. So a lot of electron partying. There we go. And this can move up here. Oops, there's a positive charge because we have to fill that hole. So we use chlorine's electrons, and then the molecule will be like this. Electron party up here, and the chlorine will have positive charge and a double bond. There we go. So yeah, oh wow, beautiful, isn't it? All those we just did together. Congratulations, you're now pro at resonance. And I just want to say, if you stayed all the way to the end of this video, thank you so much. So yeah, I know it's a very long video this time because there was a lot of to cover in resonance, since it's a big topic and it goes everywhere in organic chemistry, so you will see it everywhere. So yeah, I hope this video helped you, and if it did and you want more of these videos, make sure to leave a like. It will help a lot. And if you know someone who is having a hard time with resonance, share this video to them. It might help them and calm them down. And also comment what else I should cover, or just say hi in the comments below. And join the Discord server down below. We have a new Discord server with very nice people that are here to help you understand chemistry in an easy way. And yeah, join up and just chill with us. Let's grow together as a strong community. Until next time, eat well, stay hydrated.